Okay, hello everyone. So I guess we're already running 5 minutes late, so I will directly dive into this methods primer. I'm really looking forward to discussing with you a project we are conducting at GESIS right now, trying to support a bit the usage of Earth observation data. Okay, I have to. Okay. I guess you can hear me, but I guess it's important for the recording that I'm using this mic. To support the usage of Earth observation data in the social sciences, which is, I would say, a niche topic in the social sciences, which is quite obvious, I guess. But nevertheless, we see a lot of potential for that. And in this methods primer, we are going to address basically four challenges. What is Earth observation data? Why is it useful for social scientists? Where can I get the data? And how can I process the data? So I asked ChatGPT to support the communication of this topic with a few visualizations. And I'm actually quite happy how well ChatGPT is able to produce quite nice graphics. So I also heard that people are more interested in presentations if cats are on the slide. So all our scientists and students are cats. But coming back to the topic, so we will talk about these four issues in the next roughly 50 minutes. And to be honest, I'm not here for altruistic reasons. We have prepared a full 2-day course for this topic at GESIS. This will be held in April 2025. This will be like the kickoff for a new training material for Earth observation data in the social sciences. So it's called Advanced Geospatial Data Processing for Social Scientists. And if you want to join us, you can click on the link. How do you click on the link? On the slides. You download the slides, first of all. So if you're interested in using these slides, you can just go to this website here. You can download the slides, and you don't need to type along. So I will give you maybe 30 seconds to type that in if you want to access the slides. So I would definitely remind you about that course during the next 50 minutes several times. Also quickly about us. So unfortunately, it's only me today. We were planned to be both of us here. So this is me, obviously. I'm a postdoc at GESIS in Cologne. I have a PhD in political economy, and I primarily work with geographic information system on topics of environmental social sciences.
ChatGPT?
That is not ChatGPT. I mean, if ChatGPT would be able to produce this graphic, this picture of me, I mean, I would be scared. So cute cats is fine, but this picture, I would be scared. So we are currently working on a project, for example, measuring attribution of extreme weather events to climate change. We are linking survey data with data on weather patterns and extreme weather, and we're investigating how certain feedback effects for the attribution to climate change exist. I mean, we have currently the flood in Spain, so these are like horrible events, and we need to understand how this affects our societies, not just in the immediate impact, but obviously also in the long term. Stefan should be here, or wanted to be here, cannot be here for family reasons. He is our senior researcher when it comes to geographical data at GESIS, so he has built up a lot of projects at GESIS in the last years. Yeah, unfortunate for you that he's not here, because he often can answer questions I can't, but I will try my best to represent our project here for you. So let's start with these four challenges. What is Earth observation data? Starting very simple, given that I expected not all of you to be interested, hopefully yes, but not very familiar with Earth observation data. So very brief and very basic definition, that is the collected information about the Earth's physical, chemical, and biological systems. We are able to study the atmosphere, the land cover, land usage, oceans and inland waters, and biological diversity and ecosystems based on Earth observation data. And I mean, by the way, just interrupt me if you have questions, right? So we can just have the Q&A while I talk, but we also have time for Q&A afterwards. So for example, when it comes to climate and studying climate change, we have essential climate variables defined by the Global Climate Observing System. Currently, these are 55 essential climate variables, some of which I also never heard about. So I'm also a social scientist like you. But of course, I mean, some of these are very self-explanatory, and we know some, I guess, from daily life. So we will explore a few of these variables in a minute. If you need, or if you want to explore these in particular when it comes to climate, you can also check out the documentation of the ECVs below. We see application of Earth observation data in many fields, in especially industry and academia. So when it comes to environmental protection, energy management, urban planning, or all the other issues which are mentioned here on the slides. But we haven't really seen a lot of applications in the social science yet. And yeah, we want to change that. But before we go to the issue how we as social scientists can use Earth observation data, I also want to quickly delineate terminologies here. So we often see these so when I was like waiting outside, I heard someone saying, okay, I'm going to the geospatial data course. And that's not wrong, but I guess we often see these like terminologies like floating around: Earth observation data, geospatial data, remote sensing and satellite data. And it's important to understand that when we talk about Earth observation data, as defined before, it's the information collected about the Earth system. Geospatial data, a terminology very closely related, just relates to all information which is georeferenced, which can be Earth observation data, but doesn't necessarily need to be Earth observation data. Yeah, we will have a few examples about that in a minute. Remote sensing, information that is acquired by sensors from distance, in contrast to in situ sensors, which are local sensors like weather station, pollution monitor stations. And then satellite data, which is in the end a subset of remote sensing. We have other forms of remote sensing like aerial carriers, drones, which we can use to acquire data. So if we talk about Earth observation data, I guess for us, A, B, and C, these areas are most important, generating data which we can use for utilization in social science research projects. C, for example, is quite interesting. These are like also data streams which are not generated by remote sensing, but as I said before, in situ local sensors. And then equally important for us as social scientists is D, the geodata which we often have, which we want to link to Earth observation data, right? So maybe you have georeferenced survey data, you have georeferenced economic accounts. So all this data, of course, for us as social scientists, equally important as the other side of the coin when it comes to studying interactions between the Earth system and social measures. Yeah, so you can check that out on the slides. So that was like a very brief and very quick definition of how we define Earth observation data. I guess, and again, if you have questions, let me know. More important right now is, why is it useful for us as social scientists? And I guess if I have to choose which challenge is the biggest one, it's probably this one, right? So, I mean, we call this course Working with Earth Observation in R, but to be honest, like, it's not that tricky to work with Earth observation in R if you are like proficient in R, right? So that's like, of course, there are a few other techniques, but in the end, it's the technical process which you can learn. But having a good research question, which utilizes Earth observation data for your research project, is much more tricky and is probably the difference between being a niche product or being much more relevant in the social sciences. So this is my pitch for why this data is important for social scientists. It's also interesting that ChatGPT thinks social scientists wear lab coats, right? So I specifically asked for social scientist cats and not natural science cats. But even social scientists wear lab coats. But it's still, I guess, a very good representation of measuring the Earth. So I guess that's quite nice. We organized workshops on Earth observation data and the social sciences. We had a large one last year, and we will also have another one next year. And I guess we brought together those researchers who are currently utilizing Earth observation data for their projects very well. And our I guess our understanding of this data, where it can be useful, are basically 4 topics: environmental attitudes and behavior. We have a lot of research on that, where we link certain Earth indicators to indicators of environmental attitudes and behavior. Economic development and inequality. Especially important here are nighttime lights, which can be utilized to measure a proxy for GDP, a proxy for certain other economic development indicators. Conflict and migration, so spotting violent conflicts, spotting, I don't know, one researcher at our workshop will present a paper on migration flows in the Mediterranean Sea with satellite data. And then political behavior, how certain Earth system dynamics affect voting behavior. So we have a lot of literature on that. So, I mean, I would be happy if you now stand up and say, okay, that's not all. I'm working on a different project. So, I mean, convince me that there are other issues where we can utilize Earth observation data in the social sciences. But for now, I guess that's it. And I just want to quickly show you 3 papers which came out in the last years, which utilize Earth observation data to some extent. All 3 papers highly published. So I guess that's a plus, I hope, for pitching this data, because of course it sounds innovative. And yeah, if it's done well, like here, for example, I guess it has high value. So this one is Hoffman et al. 2022 in Nature Climate Change. And they analyze how the experience of climate anomalies and extremes influences environmental attitudes and vote intention in Europe. And they integrate data from basically 3 sources. They harmonize Eurobarometer data, which I guess was already a very major benefit of this project. They also use EU parliamentary electoral data, and they use climatological data. They aggregated this data on the regional level, and for the climate data, they use Error 5 reanalysis data, which we will talk about in a minute, which is simulated reanalysis data from the Copernicus Climate Change Service. So they calculated some kind of temperature anomalies and extremes in reference to a baseline period, and they find evidence for an effect of these temperature anomalies on environmental concern and vote intention in Europe. With a similar approach, so I will not dig very deep into this topic here again, because the EO data part is very similar from Error 5 reanalysis. Garcia Leon and colleagues utilized this data to measure how historical heat waves affected economic outcomes. So in particular, productivity and GDP. They also find some kind of evidence for heat waves affecting, basically decreasing European GDP, especially impacting highly vulnerable regions. And then the third one, which is maybe not so, I guess, obvious when we talk about Earth observation data in the beginning, but which has been also cited a lot, and which basically also sparked follow-up papers, is the utilization of nighttime lights to measure inequality and to measure economic development. So here, Jean et al., they use nighttime lights from a US DMSP project, which is associated with NOAA. So this is data on how illuminated regions are in the night as a proxy to measure economic development in countries where it's hard to measure economic development because official accounts are often not existent or not very well established, especially on the regional and local level. So I hope for those of you who have never seen applications of Earth observation data in the social sciences, these are 3 typical examples of how we can utilize this data for our projects. And I hope that there will be many more in the next years, and I hope that some of you will also find ways to utilize this data for your projects. So the first two challenges, I guess, are more abstract when it comes to understanding what it is and what is it for social scientists. Now we come to the more practical issues. Where can I get the data? Also often a very large issue. So even if you know what it is and you want to utilize it, you are not really familiar with where to get the data from. And I guess that's my favorite visualization, actually, because, I mean, visualizing the RP as a package where the data is stored and also having these cables, and I mean, cats would definitely play around with the package and the cables, so that's super correct, actually. So where do we get this data? I want to just focus on one specific source, because this is the source we are utilizing a lot in our project, and which is, I guess, from the European context, also the most relevant one, which is the Copernicus project by the European Commission in collaboration with ESA and EUMETSAT. They basically access the Sentinel fleet, which are several satellites from ESA in combination with local sensors to generate this large amount of data. So I guess they say on their website it's 12 terabytes a day they produce monitoring the Earth. And I guess like often we have these like issues where, I don't know, like in European infrastructure projects, we cannot compete with the US. So in this context, I guess we can compete. So this project is really strong, produces a lot of data, and the important issue here is it's mainly free for access for us researchers, and not just researchers, for the public itself. So given its complexity, Copernicus has been separated into different services: atmosphere, marine, land, climate change, and emergency. In our project, we are primarily working with climate change data and atmosphere data. So atmosphere data, very important also for measuring pollution, the typical pollution indicators. The climate change service to access weather data, to access other atmosphere indicators. In the emergency service, you can access data on wildfires primarily. And the land service, also very important, producing a lot of data on land usage, land cover. So the links, you can check that out. They basically all lead right now to a new data space, to a new data API, which, I mean, they are separate stores, but you only need one account. So we can also check that out if you're interested in that. So you have to set up one account. You can access the API very easily, actually. Get a lot of interesting data for your projects. Of course, this is not the only project which is relevant for using Earth observation data in the social sciences. The Landsat program is basically the US equivalent. It's also longer running, I guess. It's much older. And if you check out the Google's Earth Engine cloud computing platform, it's basically a catalog of data sets from various resources, which you can also maybe explore on your own if you're interested in that. Okay, just to maybe also highlight a bit that working with this data, let's say for the typical social scientist who is accustomed with, I have my data frame, I have my rows, my variables are columns, we are leaving this idea a bit, and we have to also face a few other data quality issues here when it comes not just to the indicator type, which is like, which kind of indicator am I using, but we also talk about spatial resolution, temporal resolution, so how fine-grained is the data, and we will have a few examples about that in a minute. The spatial and temporal scope, sometimes also called coverage, so how long-running is my data, temporally, but also spatially, so how well covered is my data? Is it about the entire Earth? Is it about Europe? Is it about a specific country, or more fine-grained? The types of measurement, the providers, the sources, the API, and the costs. And just to, I guess that is always very helpful, because people really like, they are struggling with like understanding like how much do I have to pay, like how good is the data, right? And there was like one project by the German Federal Statistics Office a few years ago where they also compared products to investigate how suitable is Earth observation data in federal as proxies for federal account statistics. So not just some ivory tower research project, but the Federal Statistics Office really is like thinking about utilizing this data as proxies. And I mean, Sentinel-2 here is like the EU project satellite with a resolution of 10 meters. But we have commercial proprietary products which are much better when it comes to the resolution. The frequency, it really differs even for the public data. So we have public data in Copernicus which has a very high frequency. But yeah.
Yeah, just a quick question. I mean, you said before you mentioned these aggregation up to the NUTS regions, I think, for 2 papers here in Europe. I mean, what's the point of having a resolution of 0.3 meters if I, as a social scientist, anyway need a much larger kind of area to which I apply the whole thing to then?
Yeah, I mean, that's a really good question. And I guess in the end, it depends on your research question, right? So that's why I wanted to show you this one on the next slide. I mean, on the left-hand side, they basically produce a picture which has a resolution of 30 centimeters, which conforms to the product by Worldview, by the Worldview satellite. And on the right-hand side, we have a resolution of 10 meters, which represents, as an example, Sentinel data, right, which we can publicly access today and we can just utilize for our projects. So, of course, I mean, what's your question, right? If my question is, I want to use this data, I want to use a machine learning classifier to count the number of containers as a proxy for economic activity. With the Sentinel data, it will probably be quite difficult, right? With this data, it is definitely possible. So, I mean, that is like a struggle we have, of course, that the data quality really limits the questions you can ask with the data. On the other hand, I would also say, and I mean, maybe it's also important to note, when we say Earth observation data, often we are not referring to satellite images which we then classify ourselves. So we are already accessing not just the raw product, but refined products, which is called level 3 or level 4 products, which are derived from these satellite images, and we just access the data stream of, for example, a pollution indicator or any atmospheric content. But yeah, of course, so this is just like to exemplify for you, like, do I have to pay to find data for my research question, or can I use the publicly available one? And of course, on the right-hand side, if my question is just counting, for example, cargo ships in the ocean as an indicator for economic activity, it might be possible with Sentinel data. So maybe you can identify cargo ships. You cannot count the exact number of containers, but you can identify cargo ships in the harbor, in the ocean. So I hope that this gives you an indication about the quality when it comes to publicly available data and privately available data, and that you need probably a very large research grant if you want to work with a high-resolution data. Okay, so I guess that was roughly 30 minutes. Let me check. Yes, so it's exactly 10:30. So if there are no questions on these more general issues here when it comes to Earth observation data, I want to spend the rest of the session on the how can I process the data. And of course, I mean, we had to like decide how much can we go into detail, given that this is like probably just a pitch for methods training. This is really just like a light introduction, an overview about, I assume many of you work with R. So R is not the issue, but probably like this data type is the issue for you, the new issue. So I just want to pitch you a bit like, where do I have to look in R to work with Earth observation data, which maybe is a bit different than the typical row column-wise data frame we normally use in social sciences. So, also very good. I mean, what ChatGPT produced here for like the R working environment, not bad, I guess. Yeah, so R, again, I hope I don't have to pitch R to you, but if I have to pitch R to you, then it's free and open source, and we have a lot of packages which help us, not just with Earth observation data, but the entire geospatial data realm, right? And the not so easy thing for me when pitching Earth observation data in R is the fact that it's basically about the first part of this tidy workflow, right? So this is like from R for Data Science, from Haley Wickham, and like this logic of like doing the entire work in R. I would say, when talking about Earth observation data, the new stuff comes when it comes to tidying and transforming data, because raster data is a bit different than our typical data sets. The second part, visualization, modeling, communication, often is very similar to what you know already. And pitching, data wrangling is not very fancy. No one, I mean, visualization, analysis, fancy models is probably a bit more interesting than showing you how to process data, right? But that's really what we have to talk about here. And just to briefly introduce for those of you who are not so familiar with that, so why is Earth observation data for us a challenge in R? Because I guess like the basic geospatial data training in R starts with, this is a vector. And here you have a polygon, you have a point, you have a line. And you work with these data structures, so points, lines, and polygons as vector data when you learn geospatial data manipulation in R. But Earth observation data is primarily stored in grids, which is like raster data. So there are a few differences and a few similarities here. And maybe you know grids from other data sources, sometimes socioeconomic, sociodemographic. Geospatial data is also stored in raster data and grids, so it's maybe not completely new to you, but for many who we talk to, this is completely new. And it's new and it's challenging because you have different data formats, you have different file extensions. But on the other hand, the geometries also do not differ within one data set. So here, of course, a polygon, if you have polygons of countries in the world, each polygon differs, right? Because the shapes of the countries are different. Our grids are uniform. This can be more efficient because we have like this more global metadata instead of like observation-specific metadata, and we have straightforward processes to process these raster values. So you can, in the end, it's working with working with simple tabular data. To show you how this looks like here. Imagine you have like a data on pollution levels, whatever metric this is. We basically just store each of these values in a cell, which represents the position in the grid. So why is this geospatial data? Oh, maybe first of all, as I said before, the geometries are globally stored. We will see that in a minute in our data set. They are not like observation specific. They are same for all observations. And the location in space is defined by the cell location in the data table. Without this information, this would just be an image file. But because we add this metadata, it becomes a geographically georeferenced data set. So what are the important metadata here? The number of columns, rows, and cells. So these are the raster dimensions. The extent. So this is similar to a bounding box in a vector data. And to be honest, I mean, so I guess we use that very synonymously, even if probably it's not correct, but bounding box and an extent is very synonymous to me. The resolution, we talked about the resolution before, and you have seen that, of course, if the pixels are smaller, you can detect containers. If the resolution is larger, the pixels are larger, and you cannot detect the container anymore. And then we have the coordinate reference system, which is always like a struggle for social scientists and also for me. So it defines where on the Earth's surface the raster layer lies. And we have all these different forms of coordinate reference systems. You have to like transform maybe and transform coordinate reference systems if you were working with two different data sets who have different reference systems. That is, yeah, sometimes quite challenging in our long training course. In April, we will talk a bit more about this and, yeah, give you a bit more input into this. Okay, so yeah, this is, I guess that is like the core information you need when you want to work with Earth observation data in R, that you have to face the fact that you have to work with raster data. And it becomes a bit more complicated because it's not just raster data, but it's data cubes. So it's a stack of rasters into an n-dimensional data cube. And then it becomes really a bit more complicated, but that is like really the technical part which is important for you when working with Earth observation data in R. The nice thing is, and I mean you know that from other stuff in R, you don't have to do this all manually in R, right? So other very smart colleagues have produced very, very helpful packages for us which help us to work with this data. And probably the most established one, the most important one is Terra by Robert Heijmans and its predecessor raster. And I mean, so we said probably the most commonly used because we did not measure but I mean, all people we talk to, they use Terra. So yeah, so that is like the starting point for you. And I really want you, I mean, if you want to work with that, you should really check out that tutorial here. You can click on the link. It's basically like a textbook, right? So they have basically produced a textbook for free for us, for spatial data science in R, based on their Terra syntax. But, and that is like not the alternative, I wouldn't say alternative, but an addition or, yeah, I have to think about how to pitch this package. It's called STARS. That is like, that is produced by Edsa Pebesma, and it has been produced especially for handling spatial temporal arrays. So arrays are data cubes, stacked raster layers. It's a bit newer. It's a bit, let's say, more into this tidyverse logic. So you know from this discussion about base R and tidyverse, STARS has the same logic and syntax like the SF package, which we use for vector data. And in combination, STARS and SF basically is like the new geospatial tidyverse. So that's quite nice, actually. And you can check that out. Similarly, they have also produced a textbook, Spatial Data Science, also super helpful, not just for working with Earth observation data, but just like as a very, very, very good textbook on this topic. So our examples today are based on Terra, but they can be equally reproduced with STARS. And yeah, you can check out both. And I guess in our daily work, we use both, right? So it's not that you have to choose. So I guess there was even a blog post by Edsa Pebesma who said that actually he would have preferred that there's just one package. I guess he's also a contributor to Terra, but somehow it developed into two separate packages and two separate logics, which is a bit unfortunate for us users. Okay, so the remaining time, I just want to show you how we can like work with raster data a bit in R. So I will show you a few examples to familiarize you a bit with these issues, and then we're already done. So the beginning is quite easy, or the starting point here. Using the Terra package here, there's this function rust to just set up an empty raster file as a spatial raster class. And here, this is important to note. In contrast to vector data, the metadata is stored globally for this entire file here with the dimensions, the resolution, because it's empty, it's just one, the extent, and longitude and latitude with WGS84 as default. Yeah, so I guess that is quite self-explanatory. If we input here a sample of 16 values taken out from values from 1 to 100, and we create a matrix with 4 rows, and we assign this input data to our raster file. We can see that we have basically inputted these values to our raster file. And I guess what has changed here, the extent, because it understands the number of rows and column, and the definition of minimum maximum values, which are just randomly sampled from our sample here. Yeah, we can plot this raster very quickly with the plot function in Terra. And I mean, in the end, I mean, that is already, when it comes to visualization, that's not it. So in our 2-day course, we will talk a lot about integrating and plotting Earth observation data with ggplot. For now, we will just use the default plot functions in Terra and the tmap function. But yeah, I mean, this is already, if this would be real-world data, this would already be the visualization of your Earth observation data. But it's not, it's just like randomly sampled. As I said before, we can use the tmap package with the tm shape function to plot raster layers as well, so that is really helpful actually. So if you don't know the tmap package, you can also check that out. Oh, it's actually not linked here, but okay, you can Google that. And tmap is often used for raster files. Okay.
Maybe I missed that. So these 4x4 boxes that you show us there, or rasters, where on Earth is that now located, or is that?
So this is just randomly sampled data, and because it's randomly sampled, and it doesn't, I mean, it's not located on Earth at all because it doesn't have a coordinate reference system here. We have assigned this random data points to our raster layer, and you can see here that the coordinate reference system has been removed because it doesn't conform to the coordinate reference system, so it's just random data points. And in the next step, we will utilize an example data frame, which is real-world data, and then you will see how this will be plotted on Earth. But before we go into that, I just want to mention very briefly again, I mean, we have different data files here. And raster files often, if they are like simple raster files, they are stored in TIFF or GeoTIFF. And again, if there is no geo part, it's just a TIFF, it's just an image, right? But because we have this geographical referencing, it's a GeoTIFF. You will also come across GRIB and NetCDF, which is often used in Earth observation data to store large data cubes. So I guess these are the most used one from my perspective. Okay. So in R, loading this data, I've just downloaded from the ERA5 reanalysis, which is a very nice simulation project by Copernicus using real-world observations to generate a long-running historical data on a lot of indicators, weather data, for example. So this is like not real-world data. This is simulated data based on the best available real-world observations. I've just taken out 2 raster files for temperature for June and July 2019. So with Terra, we can just read it in with the raster function. It's stored here in my data folder. And we can see that when loading these objects and opening this object here, you can now see that the global metadata is also a bit different, right? It has dimensions, 561 rows, 1,440 columns, and 1 layer. And this is important because it's just one raster file. As soon as it becomes a data cube, there will be more layers. So we basically stack up our data set. It reports the resolution in degrees, 0.25 by 0.25. The extent, you can see here that's basically global data. The coordinate reference system, and importantly, it also understands that there's a value attached to these raster files, which is defined basically here by the name. 2 meter temperature, minimum values and maximum values. Actually here the C is not correct, it's in Kelvin for now, so that's why the values are so high. again, we can plot the data, and now this, in the end, it's the same as like the 4x4 raster you've seen before, but of course now, because you have so many raster cells, it looks like a very nice visualization. We don't have much time to go into detail into all these transformations we can do. Of course, the Terra package offers methods for global statistics, for local statistics. It offers methods for transforming the data. And I just want to show you a few now to give you an indication what you can do. For example, you can very speedily compute global statistics, like here the mean. So you know the R syntax. You first have the function global. Your first attribute is the data you input. The function attribute defines the function you want to perform, and then the attribute on the removal of the NAs. Here, not so important. I guess there are no NAs. There shouldn't be any NAs. To calculate a mean for the entire world for June 2019, the average of the averages. Matrix calculation and raster calculation will be a larger topic in our 2-day course, where we go all through, will go through these typical transformations of raster files. For example, it's in Kelvin. No one understands Kelvin. What does it mean? So if you want to convert it to Celsius, you subtract 273.15, which is quite straightforward here in R, where you can just subtract a constant value from your raster file, and basically subtracts it from all cells individually. So you can now see nothing has changed in our global metadata here, except for the minimum maximum values for June 2019, which are now set to our more humanly understandable Celsius values. Oh, that is actually a bit shifted. Okay, these calculations can also be transformed between rasters. Here, the subtraction of June from July to calculate differences in cells, so the temperature differences in the average between 2 months. Again, our metadata has not changed, and the minimum and maximum values report for each cell the difference increase or decrease between June and July in the aggregate averages in these raster cells. Okay, so I guess like this calculation, not very interesting, not very good issues for pitching why Earth observation data is important for us. I hope that this is a bit more interesting for you, because now what we normally want to do as social scientists, we are studying countries, we are studying regions, we are studying, I don't know, individual respondents, and these are normally stored in vector data, right? So it's a point, it's a polygon, or sometimes it's a line, but again, I guess I haven't seen many like line operations in social sciences in the last years, but in papers, but importantly, polygons and points. So, for example, we are in Belgium. I have created a vector for Belgium. You can check that out on the left-hand side. There is like this nice package called R Natural Earth. It is suitable to just download vectors for the entire globe. And I've subsetted here to only the geometry for Belgium. So that is like our vector now. And we basically have 2 important transformations here, which we have to perform: cropping and masking. So cropping is basically slicing our raster data to the extent of our geometry. And it's very easily done in Terra, or with Terra, with the crop function, where our input here is our raster file first, and then our vector data secondly, as second attribute. And if we do that now, you can see here the data has been like cropped to the extent of the raster file. Of course, I mean, it doesn't crop to the exact outline of Belgium, it's just using the extent of the vector. That is already a good starting point, but then of course we also want to like remove all values which are not part of the Belgium vector, because we don't want to include raster cells from the Netherlands which border Belgium. So we do masking, we use masking. Similarly easy in R with the Terra package here, mask. Similar syntax, the attribute and the vector here. And of course, if we just perform masking, we didn't do cropping yet, we have the full extent of the world of our raster file. And the small dot here, you can see how large Belgium is our masked raster cells for Belgium. So what we normally have to do is we combine cropping and masking. And the nice thing about Terra is that it is suitable for our piping operations, like I assume many of you know in R, so we have the pipe here. We can just pipe our object into crop and then pipe the output into mask. And if we do that, we finally get what we want to do. We only get the raster cells for Belgium. Yeah, so this is how Belgium looks like when it comes to temperature in June 2019. Yeah, so this is a good starting point, I guess, to understand how we can extract this data for our purposes. You will have a project where you maybe have a different vector, but it will most of the time boil down to this operation. Okay, so given that we are lagging behind a bit, I will just very briefly go through this issue here. Of course, this was an example for a polygon. This one is an example for points, so I'm just sampling random points here. We don't have to discuss in detail how we do this. We just sample from the raster file 10 random points. These points are located somewhere in our area. And we can extract values for these 10 points here. So we just want to have the cell value for this point, the cell value for this point, and so on. So we can extract these raster values with the extract function from Terra. Similar syntax here with our attribute, the raster file first and then the vector second, to access these 10 values for our 10 points. And then we can add it to our data set, which we can skip here by now. And now this is maybe my last point when it comes to these operations. Often we don't link one-to-one with points, but we have understanding of a spatial buffer. My person, my respondent has a certain activity space or whatever space is relevant for the buffer you want to define, and we can also do that here with the stBuffer function from the SF package to define buffers here. So since our cells are so large, there is no overlap, so the buffer really doesn't change anything here. If the buffer would overlap with several raster cells, we could, for example, calculate averages across cells. Yeah, so these were a few examples for handling raster files in R. What most of you will have to do is this spatial linking. So this is really this crucial step in most of the research projects. All papers I've presented do spatial linking. They have to somehow integrate the data. And when they integrate the data, they have to somehow define how they integrate the data. And this, of course, for those of you who are interested in geographical data analysis, is prone to certain ecological fallacies, modified areal unit problem, the uncertain geographic context problem. So a misfit, in simple terms, a misfit between the true data generating process of the buffer, so in reality, which we will never know, and how we define the buffer. The technical part is not very challenging. The technical part has been defined in many projects and can be done very easily. We will actually offer a package which will help you in this integration, the access to the Earth observation data, the aggregation, and the link. It will be published as a service by GESIS in the beginning of next year. And I will also give you a few hints at the end how you can access the data, access the package. So the technical part will be supported with this package. The theoretical part and all these ecological fallacies, not so much. So this is really your task still. We will focus on, in our package, on supporting you in selecting the indicator type, the indicator intensity. So do you want to calculate certain deviations from a mean, anomalies, extremes, and so on. The focal time period, so what is like the time period I want to link to. The baseline time period, what kind of information is my reference information. and the spatial buffers. So is it like a small buffer? Is it a large buffer? Do I use vector geometries like regions or countries? Okay, and now the turn from raster data to Earth observation data is just one additional dimension, and this dimension is the layer, right? So Earth observation data is often stored in data cubes, which we call arrays in our terminology. And with our two raster files, temperature 6, so June, and temperature 7, July, if we just concatenate with the C function into a new object, this is basically now a data cube. You can see here, n layer is 2, and the data is stored in a 3-dimensional space now. And this is like the only challenge we really have, or not the only challenge, but the major challenge when we're working with Earth observation data and data cubes, that the data looks like this, and it can become n-dimensional. And we as humans have difficulties when it comes to more than 3 dimensions. So that is often a challenge for us. But we will discuss a lot of these issues in our course and how we can, find ways to work with this data. Okay, so I had to speed up a bit because we started a bit later. We have 3 minutes left. I just want to pitch a few things to you now. So first of all, if you're interested in updates on our package, on our training modules, on our workshop, just send me an email. We have a mailing list since we have created this project. We're working on this project now for 1.5 years, so we have roughly 50 colleagues from all over the world on the mailing list, and every time we organize something or we see something which is interesting, we send out an email. So send us an email if you're interested on updates on our project. With this email, you will also get the update once our package is out. More importantly, because it's very topical, next month there will be a workshop at GESIS. 3 days just discussing Earth observation data and the social sciences. We have 2 very interesting keynote speeches by Jennifer Marlon, who's the executive director of the Yale Center for Geospatial Solutions, and Al Daoud from Linköping University. We have a data quality roundtable, and we have many interesting presentations on questions like, do earthquakes affect voting outcomes? What political and socioeconomic factors affect the distribution of pollution monitoring sensors? Or do autocracies misreport GDP accounts? And can we measure how much they misreport? So again, the schedule is set. If you're interested in participating in the audience, send me an email. We have a few spots left. I guess I would say first come, first serve. And then I just want to mention again, we have our training workshop. So this was the primer for 2 full days with us, with Stefan and me, online actually in April. You can click on the links to sign up to this course. There's also an introductory course a few weeks earlier by Stefan and a colleague Anne, if you want to have a more more simpler introduction into geospatial operations and primarily vector data, right? So if you want to start with vector data and then 2 weeks later join us for raster data, you can check out both courses. And Tobias Guttenauer is also teaching a geodata and spatial regression analysis course in July at GESIS. So if you're interested in spatial econometrics, you should definitely also check that out. I just want to say finally that you actually don't need us. That is the really nice part about R. It's free and open source. And I just want to mention again the 2 textbooks, which I've mentioned when we talked about the 2 packages, Terra and Stars. These are super helpful. And yeah, of course, much of the content we are using in our training modules is also based on these textbooks. So I can only recommend these. Yeah, I'm really sorry that we don't have much time left for Q&A. But yeah, we started 5 minutes late, so I would say we have 5 minutes for Q&A.